Rules of equivalency. Just like we have rules of equivalency for two-dimensional shapes, there are rules of equivalency for three-dimensional solids. If you have equivalent solids with the same number of faces, the regular solid will always have the smallest surface area. So remember, a regular solid is a solid where each face has the same shape and size. Second rule, if you have two solids with the same number of faces and the same surface area, the regular solid will have the greatest volume. So this rule again is very similar to the rule when we had two-dimensional shapes. A regular two-dimensional shape has a greater area, or has the greatest area, compared to a shape with the same number of faces that are not regular in size. If you have equivalent solids, the one with the greatest number of faces will always have the smallest surface area. If you have solids with the same surface area, the one with the most faces will have the greatest volume. When I talked about the solutions to question 10 earlier on when we were dealing with the rules of equivalency for two-dimensional shapes, I talked about how the closer things got to being a circle, the more efficient it basically became. So you were maximizing area and minimizing the perimeter the closer you got to a circle. So that meant that a octagon with 8 sides was closer to being a circle, and therefore if it had the same area as a pentagon, so a 5-sided shape, it would have a smaller perimeter. And similarly, if the perimeter on an octagon was the same as the perimeter on a pentagon, then the area of the octagon would be greater than that of the pentagon. So now we're dealing with something similar. If the closer you get to being the shape of a sphere, the more efficient you are as far as minimizing surface area and maximizing volume. Let's look at a couple of examples. So we're given that the following solids have the same number of faces and the same surface area. Which one will have the greatest volume? So in this case, if you remember rule number 2, it tells us that if you have solids with the same number of faces and the same surface area, which is what we're given here, we have the same number of faces and the same surface area, when that's the case, the regular solid will have the greatest volume. So in this case, the cube is a regular shape, therefore the cube has the greatest volume. Of all solids with the total volume of 8 cubic centimeters, what is the shape of the solid with the smallest total area? So if we're looking at all three-dimensional shapes, all possible solids, we have to consider prisms, pyramids, cylinders, cones, and spheres. As discussed previously, spheres give you the optimal shape when it comes to maximizing volume and minimizing surface area. So if you take all the shapes that have an 8 cubic centimeter volume, the one with the smallest surface area will be a sphere. So effectively, rule number 3 comes into play here, where if you have equivalent solids, the one with the greatest number of faces will always have the smallest surface area. In this case, a sphere effectively has almost an infinite number of surface areas. So as a result, when you're dealing with equivalent solids that have the same volume, it will have the smallest surface area. Add this to your memory aid. Try the practice questions in the workbook and check your answers against the answer key.